It's the time of the year to get together. Sadly this time around virtually. Let's make the most of it, we always do. Hooray! For ICPS 2021. For exciting days are ahead of us. We've been waiting for this so long. Let's connect again, our physics friends. Cause it's ICPS 2021. Let's take our time to gather all the knowledge. Brilliant speakers, we share it just with you. Collaborations, friendships, and so much more. Hooray! For ICPS 2021. For exciting days are ahead of us. We've been waiting for this for 2 years. Let's connect again, our physics friends. Cause it's ICPS 2021. Let's get to it, it's gonna be fun. ICPS. Hooray!
Hello, everyone, and welcome to the next speaker of the day. With us, we have Colin Wright, and he's a mathematician, and he's going to talk about unexpected math, in this case, in juggling. So without further ado, I think we will just give the word to Dr. Colin Wright.
Thank you very much. And thanks for all the work that you've done in making this possible, because it's fabulous to be able to join you. When you first asked me to speak years ago, we never expected the current circumstances. It's great that we could make it work. So first of all, yes, I'm a mathematician, although my PhD is a long time ago and my research is a long time ago. Most of the time these days, I'm involved with a company which you can see listed there called Denbridge Marine Limited, and they do the maritime equivalent of air traffic control. So in particular, we use land-based radar and satellite systems for communications and timestamps to monitor where ships go and make sure they move safely and securely through an area of responsibility. And I go out and I do talks. And I do talks about this for school kids, and I talk about why maths turns up here, but nobody is surprised when maths turns up in such a technical area. That's just completely expected. If you're going to do something technical, you expect to do at least some maths. And so that's no surprise, although I think it's fairly interesting, the maths that I do there. What we're trying to do is to stop this sort of thing from happening. There's a technical term for this. It's called a bad thing. And so we try and stop that from happening, as well as making sure that ships move efficiently and safely through whatever area of responsibility it might be. I do want to point out that nobody died in these particular collisions, but collisions at sea happen every year, and people do die. So I use maths to help stop people from dying. And I think that's quite a cool thing to be able to say. Of course, there's a degree of engineering in there. There's a lot of physics and there's a lot of electronics, and it's all connected. But as I say, it's no great surprise that you use maths to try and stop. Oh, I'm also very pleased to announce that our company was not involved in any of these incidents. Fortunately, no incidents have happened that we've been monitoring. Although accidents happen, you never know. And the statistics of trying to figure out what the threat analysis is, it turns out to be really important as well. So that's just a part of what I do for Denbridge Marine Limited. However, I also have a company called Solipsis Limited, and I go out and I talk to school kids and parents and teachers and all sorts of people on how maths turns up when you don't expect it. And what I'm going to show you is maths turning up in a way that you don't expect. So when I talk about the maths of juggling, people usually say, well, you're going to talk about the trajectory that it follows. It's an inverted parabola. You might talk about the energy. You might talk about the impulse. You might talk about, if you're really complicated, start talking about air resistance and turbulence. That's the expected maths that you get in here. I want to talk about the unexpected maths. Now, I don't know how many of you can juggle. If we were live, then I would actually ask people to stick their hand up and give you the promise that I would not pick on you. I would not ask you to come up and juggle, but I can't do that now. So I don't know how many of you can juggle. But what I'm going to do is I'm going to introduce you to the basic ideas in juggling. Okay, so I start off, and what a lot of people say to me, I can do 2. And what they invariably mean when they say I can do 2 is that they can do this. And usually at this point, I see lots of people nodding their heads. Yes, this is what we mean when we can juggle 2. And a lot of people can do this. It's not so difficult. If you've played a lot of sport, it's usually quite easy to do this sort of thing. But I will guarantee you something. I will guarantee that you do the throw-in with your good hand, with your right hand if you're right-handed, and with your left hand if you're left-handed. I guarantee, well, it's not quite a guarantee, but it's pretty close. It's better than a politician's promise. It's almost certainly true. So what happens here? Why do you do the throwing with your good hand? Well, a lot of people think that when you juggle, it's all about being able to catch a ball. And that turns out not to be the case, because no matter how good your catching is, if the throw is completely wild, you'll never be able to juggle. You'll end up running after things. It just doesn't work. What really matters is that the throw is perfect. If the throw is perfect, then the catch will take care of itself. If the throw is perfect, just put your hand in the right place and the catch will happen. If the throw is perfect, you don't need to be good at catching, but you do need to be good at throwing. And that's why you use your good hand to do the throwing, because that's the one that you're usually quite good at. And if you don't believe me, why would you believe me? You've never seen me before. If you don't believe me, test it. Go away, have a go at doing 2, throwing with your good hand, and then make sure nobody's watching. Have a go at throwing with your not so good hand. You will find that that is incredibly difficult. Most people at this point give up. But it's not hard if you practice. You have to practice making that throw perfect. And if you can do that, then you can juggle 2 going this way round. You can juggle 2 going this way round. So now you can swap. So you can have the ball going back and forth, and you can have it going in either direction as often as you want. And if you can do this sort of thing, you are moments away from being able to juggle 3, but not the way people expect. People expect, because you do 2 with them going around in this cyclic pattern, it's not a circle, as we know, this is a parabola. Actually, technically, that's not a parabola. Technically, it's an ellipse, because the Earth's gravitational field is not uniform. It slopes in, it gets less as you go up. So technically, it's a portion of an ellipse, unless you throw really hard, in which case you can get a big hyperbole, but no, you're not going to throw that hard. So the thing is, the path of the ball over small distances, we approximate it as a parabola, but it goes around in a cycle. And so people think that the way you're going to juggle 3 is to have the balls go around in a cycle. Now this is hard. This is really hard. And if you listen to it, tick, 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 you can hear just how difficult that is. And one of the reasons that that's hard is because every time a ball goes into the air, you then have to handle it twice before it goes back into the air. So as it comes down, you catch it over here, you pass it across over there, and you throw it back up. I'm lazy. I'm not going to handle it twice. When the ball comes down, I'm going to throw it back up again. And so that's what I do. So here I am. I've got 2 in this hand and 1 in this hand. I want you to imagine that I've got 1 ball in each hand and 1 in the air. So here's the one in the, actually, the green ball is here. Okay, remember that. The green ball is here in my hand. Okay, so here we go. The pink ball is here, the orange ball is here, and it's coming down, and it's coming down, and it's coming down. But this hand has a pink ball in it. It's coming down, it's coming down. What do you do with the pink ball? Somebody recently said, throw it away. Okay, you can throw it away, but then you have to run after it. That leads to a sport that we call joggling. You're not going to do that. As this one comes down, you do throw it. Don't throw it away. And you can't throw it over there because this hand still has the green ball in it. So as this comes down, you throw this. But where do you throw it? You throw it straight up, because then it will be easy to catch. So I've thrown this one straight up. It's here in the air. It's coming down to the hand that's holding the green ball. It's coming down. So what do I do with the green ball? I throw it straight up so that it's easy to catch. And if I keep doing that, I end up much, much gentler, much slower, much, much easier. And after a while, this gets really boring. So I bring it down and I widen it out, and that ends up with 3 in the easy way of doing it. And it's so slow when you're used to it, when you're good at it, when you've done it as much as I have. But you can see here, it's not a circle. If you watch one of the balls, if you watch the green ball, you'll see that it goes up in the middle, down the outside, up in the middle, down the outside, up in the middle, down the outside, up, unless, of course, you drop it, or up in the middle, down the outside, up in the middle, unless it goes up on the outside, down in the middle, up on the outside, down. We'll come back to that later. So it goes up in the middle, down the outside, up in the middle, down the outside, and that doesn't look like a circle. It's a figure of 8 lying on its side, but it is a circle. It's just that it's a circle with a twist in it. And if you take a big loop of wire and put a half a twist in it, you end up with this figure of 8. You end up with the shape that the balls make going around in this pattern. And that's the easy way to juggle 3. And people do say, well, you know, how many can you do? Well, I used to be able to do 5. I used to be able to do 7. I can still pretty much do 5, and I hope to show you that later. But the interesting thing is, doing more is not what you have to do. Once you can juggle 3 in that pattern, there are many, many more things that you can do with just 3. So for example, you can take one, the orange ball, and instead of throwing it in the middle, you can throw it so it goes over the top. I don't know if you saw that. Let me do it again. Throw the green ball over the top, the green ball over the top, the green ball over the top the other way. So I can now throw the green ball over the top the other way. In fact, I can throw all of them over the top that way. I can throw all of them over the top that way. I can throw one ball backwards and forwards over the top. I can throw all of them over the top in both directions. And if you take the time, if you take a video of this and play it backwards, you end up with this. Throwing over the top with both hands all the time is the same as the normal pattern running backwards. But that's not all that you can do. You can take one of them and, for example, you don't have to throw it at all. You can just hold it, make it go up and down, make it weave in and out, make it pretend to follow the orange ball. You can drop it. You can do a huge number of tricks. You can take one and you can chop it down the middle. You can take one, I'll take the yellow ball and throw it under the arm. Under the arm. And if you do that on every throw, I think that looks quite good. But I have just lied to you. This is not every throw under the other arm. This is only every throw with this hand under the other arm. What happens if you also do every throw with this hand under the other arm? And not just for a while there and a while there, but every throw with every ball. And you end up with this. Which is just insane. So I was learning to juggle. I wanted to learn 5. 5 is hard. 5 is really hard. And after about 20 minutes of trying it, I was hot, tired, frustrated, and angry. I knew what I should do. I knew what the pattern was. I knew what I had to make the balls do, but I couldn't do it. And when I stopped and looked around the room, nobody else was juggling 5. Everybody was juggling 3. And they were doing patterns like I'd just shown you. So I took out a notebook and I went and I wrote down all of the patterns. One over the top this way, one over the top this way, constantly this way, back and forth. And I wrote all of these things down, including throw one behind the back, throw one under the leg, throw one under the other arm, which I've shown you. And then I went up to somebody. I went up to a guy called Mike Day, and I said to Mike, show me a 3-ball trick. And Mike had been watching me. And he had seen that while I was writing down all of the tricks, I wasn't trying to do them. And he said, you want to learn this. So I stood there with my pen poised above the paper, ready to write down what he was doing. And after a while, I said, what are you doing? And he said, it's called Mill's Mess. So I wrote down Mill's Mess. And after a while, I said, yeah, but what are you actually doing? And he said, well, it's 3 consecutive throws from this side of the body into the middle, followed by 3 consecutive throws from this side of the body into the middle. Let me try and help you see that. I'm going to do this again. I'm going to call the colors as they come up on this side. So here we go. Orange, green, yellow. 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 Now look on the other side. Orange, green, yellow. 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 Orange, green. Does that help? Well, it didn't help me. I wrote it down and I came back later and I said to Mike, I can think of 3 different ways of juggling 3 balls with 3 throws on each side. And Mike thought for a while and he said, I can think of 5. And it turned out that one of the ones I had, he didn't have. So that gave us 6 ways. And we thought 3 balls, 2 hands, 2 times 3 is 6. There's 6 ways of doing this. That makes sense. And then a chap called Adam came along and he said, I can think of another one. And that gave us 7. There is no nice way to make 7 out of 2 and 3. But we thought for a while and we found another one and that gave us 8. And there's a lovely way to make 8 out of 2 and 3. Take 2 to the power of 3. And never mind why that's true, but 2 to the power of 3 is 8. And we thought, we've got it. And Adam then said, why is it 2 to the power of 3 and not 3 to the power of 2, which would give us 9? Maybe there's another one. And we pointed out that they came in pairs, like particles and antiparticles. They're sort of matched up. And so that would mean that there's an even number. And then he said, well, maybe it's its own antiparticle. Maybe there's a trick that's its own friend. We all know people who are their own best friend. So we thought, maybe that's actually, well, we hunted. We couldn't find another one. So we had 8. And we ended up proving that there is 8 ways of juggling with 3 throws on each side. But to do that, the question then arises, A, what are they? And B, how do you describe them? How do you write down a juggling trick? Now, no video and no film. You can just video a juggling trick, but that's basically like taking a recording of music. And we didn't want the equivalent of a recording. We wanted the equivalent of the sheet music. We wanted the ability to hand somebody a piece of paper and let them read the piece of paper and reproduce the juggling trick. So we didn't want the recording. We wanted to be able to write it down. So no film, no video. How can you do this? And we figured people must have done it. I mean, juggling's been around for centuries for certain, millennia almost certainly. There are carvings in Egypt that are 3,000 years old that appear to show people juggling. So juggling's been around for a very long time. Surely somebody has figured out how to do this, how to write down juggling tricks. We can do it for dance. We can do it for language, Benesh notation and Laban notation. We can do it for language, writing. We can do it for music, as I say. How do you write down a juggling trick? So we went and we looked through all the magazines. There are magazines about juggling. Cascada, The Catch, Juggler's World. My favorite was called Throwing Up. But yeah, so there are magazines about juggling. None of them had descriptions of juggling tricks. So it looked like nobody had done this. Why? Why not? Why had nobody done this? And the answer is, it turns out to be quite complicated. It turns out to be really quite hard to do this. By the way, this diagram at the end, we will use this, and I will be able to use this to create a juggling trick to demonstrate for you. And with any luck, when we have some chat at the end, if people want to, we might be able to actually use this to generate a juggling trick. I don't know if we'll end up with enough time, and I don't know if we can make the tech work. But this is actually, oh, by the way, this is genuinely the statement of a mathematical theorem which arises from the maths of juggling. And when I show this to mathematicians, or when I tell mathematicians this, they are somewhat surprised. There is some really cool stuff going on here. I'm not going to go down that path. Ask me questions afterwards if you want to know more about that. I'd be happy to talk about it. But to do this, we need to simplify the problem. You're accustomed to this. Modeling in physics, we always simplify the problem. You know, when we model particles flying through the air, initially we ignore air resistance. We ignore the non-uniformity of the gravitational field. We simplify the problem when we're doing this sort of thing, because there are just way too many possibilities. You can throw behind the back, you can stick it under your chin, you can throw it under your leg, you can bounce it off a wall, you can throw between people. Let's simplify things. One of the unstated things here is I'm only going to talk about juggling with beanbags, with juggling balls at the moment. All of everything that I'm going to say goes through for juggling with clubs, with machetes, with fire torches, and other obscure things that you really don't want to juggle. So I'm just going to talk about juggling beanbags. So what I'm going to do is I'm going to lay down some rules, and I will only juggle those tricks that obey the rules. So what are the rules? Well, the first rule is I'm going to throw and catch in fixed positions. To say my hands are fixed does not mean that they literally don't move. If you super glue someone's hands to the table, they do find it difficult to juggle. Don't ask me how I know this for a fact, but you don't, you know, so the hands will throw in the middle and catch on the outside, and they're not allowed to do other weird stuff. In these two words, this one rule, I have eliminated everything that you think is interesting. I'm not allowed to throw over. I've even eliminated Mills Mess. Let me show you Mills Mess again. As I juggle Mills Mess, you'll see it's not an illusion. There is a big arm cross in the middle of Mills Mess. In fact, one way to learn Mills Mess is to start juggling with your arms crossed and then learn how to uncross and recross in the other direction and then swap over. So Mills Mess has been excluded by this rule. Not enough, there's more. I'm going to insist that the timing is fixed. I juggle to a fixed metronomic beat. It's true, sometimes I will speed up slightly and sometimes I'll go down. So as an example now, I don't know if you'll be able to hear this. I don't know how good the mic is. Actually, the sound on Zoom is fantastic, but it might eliminate this. But I'll show you an example where I don't have a metronomic beat. Let's see if I can do this. It's really weird, and in fact, if I try and make that an even rhythm, which I can warp the timing, which is why this is not such a bad restriction, because I can then overcome it. If I have something where the timing is fixed, I can then warp the timing to get the other stuff. So if I do the timing fixed version of that, I end up with dum 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 dum, which is really weird because it's actually a 5-beat rhythm, and most people don't know anything in a 5-beat rhythm. Almost everything's in 2/4 or 4/4, very little even in 3/4. But there is weird stuff. So anyway, I'm going to insist on the timing being fixed. So here we go. Rule number 1. I want you to remember these. Make notes or recite them. Hands fixed, timing fixed. And then rule number 3 is that my hands alternate. Now, I hated studying languages in school, but it turns out that I'm not so bad at languages. And I love finding little things like alternate in English is one of these words where if you change the emphasis, you get a different word, alternate. Although it's related, alternate means to swap, whereas alternate means the other one. There are words in English and no doubt in other language where if you change the emphasis, or as a friend of mine says, change the emphasis, you can actually get a totally different word. And you can try this in your language. Try finding a word which, if you change the emphasis, gives you a totally different word entirely. So the one that I usually say in English is entrance. And if you change entrance to entrance, it's just completely different. Language is weird. I've worked out why. It's because people use it. And people are weird. Anyway, moving on. I'm not going to give you an example where the hands don't alternate. I'll come back to that in a little while. So here we go. Hands fixed. So what does this give me? What this means is I can now start drawing a space-time diagram of juggling. And I'm going to draw this, and I've got my left hand and my right hand on the diagram. And I'm going to have time running down my diagram. To be honest, it's because it annoys physicists, but don't take that personally. I just read downwards. This is how we did it first. I don't really understand the idea of having time running upwards, but I know for some diagrams it's more useful. But this is going to make you work a little bit harder than otherwise might have to. Time will run down my diagram because we read downwards, okay? So I've got left hand and right hand, and because my hands are fixed, they're not moving. In truth, these should be distorted sine waves running down each side, but they're not. I'm just going to draw them straight because that's the simplification I'm making. Okay, simplified model, highly simplified model. So what was the second rule? I'll give you a moment, think about it. First rule, hands fixed. Second rule, timing fixed. So here we go. What does that mean? That means that I can put a line across here indicating a tick of the clock, and then another, and another, and another, and another, and so on down my diagram. And these are equally spaced in space because the ticks are equally spaced in time. And if they were raised on the screen and I ran my hand down it, you'd hear it go tick, 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 like running a stick along the railings, tick, 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 tick. And I can make some of these lines closer together and some of them further apart. So I can distort the timing later if I want to. I'm not going to, but I could. That's how I could overcome that restriction. What was the third rule? Hands alternate. Okay, I'm going to come to that in a minute. I'm not going to do it yet. I will do that shortly. Now, this is a lie. When you juggle, it's not true that your hands are full for half the time. If I juggle like a beginner, my hands are full almost all of the time. I can even hold up the juggling balls and show them to you. My hands are full almost all of the time. Look at one of the hands and you'll see that it's almost always got a juggling ball in it. But I can actually choose to have my hands full for less of the time. I can do what's called a sprung pattern, where the balls bounce out of the hand, and now my hands are empty almost all of the time. It's the same pattern, but I've changed the what we call the dwell time of the ball in the hand. I'm going, for simplicity's sake, I'm going to pick that midpoint, the Goldilocks. Not too full, not too empty, just right. So I'm going to have the hands full for half the time. And in a moment, I'm going to ask you, how often are my hands full? And I want you, genuinely, I want you. Well, you don't have to do it out loud, but I really do want you to say that your hands are full for half the time. This really does make a difference to you being able to remember, because I'm giving you huge amounts of information here. And in a little while, I'm going to tie it all together. Okay? So hands fixed, timing fixed, hands and the hands alternate. How often are the hands full? Half the time. Okay. And then the final thing I'm going to tell you here is that when you do the standard pattern, when I do the 3-ball pattern, every throw is identical to every other throw. If the balls were all colored the same, and you closed your eyes for a moment, didn't count the timing, and looked again, you would not be able to tell which ball was which. There's a symmetry about the pattern. And that turns out to be really useful to analyze a bunch of stuff. So the standard pattern, which is what I'm doing there, has all the throws identical. In a little while, we'll do non-standard patterns. But for a little while, we'll do standard patterns. So here's your quiz. How often are my hands full? And I hope you said half the time. Okay, so hands are full half the time. Brilliant. Where do the balls go on the space-time diagram when I juggle? Well, to do that, I actually have to do some juggling. So here we go. Let's look at some juggling. Here is my space-time diagram, unpopulated by juggling balls. And I'm going to juggle with orange, pink, and green. So here are my orange, pink, and green. And for free, I mean, the orange ball has to visit this hand. Actually, I don't know which way round it's going to be on the screen. I can't tell because sometimes they do mirror things with these. So you may have to mentally swap over which way I'm doing this. But I know the orange ball visits the left hand for 1 beat. So there we go. There's the orange ball in that hand. So now I want you to watch this hand. I need to go orange, pink, green. So here we go. Orange, pink, green. Orange, then the pink, then the green. Orange, pink, green. Orange, pink, green. Orange, pink, green. Now look in the other hand and recite the colors of the balls. Is it the same or different? Orange, pink, green. Orange, pink, green. It's the same. And there's a reason why it's the same. It's because the balls follow each other and they don't overtake. And because they can't overtake, whatever order they go through that corner is the same order as they go through that corner. If you follow Formula One, it's like Formula One racing at Monaco. No overtaking, okay? You always just follow each other in line, so the ordering never changes. So now I am going to ask you a trick question. This is a trick question. Which color of ball is in my hand here? I'm going to have a drink of water and I'm going to give you 10 seconds to think about it. We might have some answers in the chat. Which color of ball is in my hand at that moment there? Well, I did warn you. My laptop has just told me it's running out of battery. I forgot to plug it in. There we go. Good job, I got the warning. Okay, so which color of ball is in my hand at that moment? Well, I invite you to remember, how often are my hands full? Half the time. So if my hands are only full half the time, I cannot have my hand full immediately after the orange ball. I have to have a gap. So in fact, immediately after my orange ball, at the place where that arrow is pointing, my hand is empty. And the pink ball comes after a gap. And then I have a gap and the green ball, a gap, and the orange ball returns a gap, and the pink ball falls off the bottom of the diagram. Okay, now we know that this hand, it went orange, pink, green, orange, pink, green. And this hand, it went orange, pink, green, orange, pink, green. So we know that the orange ball visits the other hand. But where? Or when? Same thing, space-time diagram. Let me give you a hint. It's not there. Some of you might have been a bit worried about that. No, it's not there because at that moment, the ball is in the other hand. So it can't be there and it can't be there. Okay, so have a look at these spots. Can the orange ball visit? Now, probably you're jumping up and down saying, it's symmetrical, it's symmetrical. No, don't panic. I'm going to get there. Can it be in either of these two places? Is there a simple reason why it can't be in either of these two places? Yeah. What was rule number 3? What was rule number 3? Rule number 3 was that my hands alternate. And if my hands alternate, they cannot both be full at the same time. Now, that's another reason why I can't have it where the X's are, because then both hands would be full. There's a simpler reason, namely the orange ball can't be in both hands at the same time. However, my hands can't both be full at the same time, so it cannot be here or here. That leaves me 3 places. Let's have a look at this one. Can the orange ball be here? Let's try it and see what that would imply. How many orange balls am I juggling? Well, just the one. I've only got the one orange ball here, so it has to be the same one. So this ball up here has to be that one down there. So that means that the ball has to travel from one hand to the other. But now if you look, you'll see that it has to teleport back again, taking 0 time to travel from one hand. And I can do that. I can genuinely make the ball teleport from one hand to the other, because if I juggle the balls in this cyclic pattern, if you watch the orange ball, it takes a long time to go that way and then comes back, basically taking no time at all. Yes, I fudge it slightly, but in theory, I could bring my hands together and literally pass the ball from one hand to the other. I can make the ball vanish from one hand and reappear in the other just by having them in the same place. It's what you do with warp drives if you fold space, etc. But anyway, that's not what's going on here. And indeed, that's not the pattern I'm trying to draw. The pattern I'm trying to draw is the one with the figure of 8 going on. So I'm not trying to draw the one going in a circle. This is what you would do if you want to have the one going in a circle, but that's not what I'm trying to do. That's not what's happening when I have the figure of 8. So I can eliminate that, eliminate this, and I'm only left with this one. And you can see the orange ball bouncing from one hand to the other. Now, some of you may think it looks a bit like a sine wave. I'm a bit weird. You've probably figured that out already. How many of you know, well, do you know what a slinky is? And if you know what a slinky is, do you have one? I have one here. It's one of these bouncy springs, right? Very bouncy spring. And the thing about a slinky is if you stretch it out like that and look at its shadow, you can make it be an exact sine wave or cosine wave, depending on phase shifts, etc. But you can actually take a helix and make a sine wave. And I like to think of this orange ball here as being the shadow of a helix. If I put in another juggling ball here, I have 2 helices. I have a double helix. What came to your mind when I said double helix? DNA. Can you see the 2 juggling balls as the shadow of the DNA? I even have a big gap and a small gap, which mirrors the major groove and minor groove in DNA. By the way, there's a major groove and a minor groove in DNA because the 2 strands don't follow each other on the way down. The 2 strands actually go in opposite direction. Here's something for you to try. Nobody's watching you probably. Here's something I want you to try. Have a go at taking your hands and rotating them in opposite directions. I'm going to give you 30 seconds to try that. Opposite directions. If you think that's too easy, have them go in the other direction. Indeed, have one go faster than the other, but opposite directions. Have your hands go in opposite directions at different speeds and then reverse it and have them go at different speeds. And when I do this live, it's absolutely brilliant because everybody is up there having a go at this and then they laugh at me. But that's fine because I've laughed at them first. Anyway, let's put in the extra juggling ball. And what we have now is a braid. And if you take a 3-ball juggling trick and push it through space, you end up creating a braid. And I have a friend who is not imaginary, who makes 3D printed objects of juggling tricks. I picked up the wrong one. So he actually makes 3D printed juggling patterns. And you can see there just about, if I get that against my dark shirt and I get it lined up, you can see the 2 arcs of the balls traveling from one side to the other. But he makes 3D printed juggling tricks. The one across the top there is the ordinary cascade. The one on the right-hand side is Mills Mess. And you can see 3 throws coming up from one side and 3 throws coming up from the other side. So we can take juggling tricks and push them through space. We've learned things using 3D printing technology. We've learned things about an art form that's been around for 4,000 or 5,000 years. By combining the underlying maths and physics and latest technology, we've learned new things, which is just kind of cool. So anyway, here, the 3 balls on the space-time diagram form a braid, and we can have a model of that. But now look at a single flight of the juggling ball from the throw to the catch, the green ball, as it travels from left to right, and ask, how long does that take? How long is the ball in flight? What is the time of flight of that juggling ball? And you'll easily be able to say, well, that takes 2 beats. Yeah, not a problem. My comment at that point is I don't care. Why don't I care? Well, jugglers don't care about the catches. This is a catch. Jugglers don't care about the catches. Jugglers only care about the throws. And if you look at the time from throw to throw and ask how many beats of time is it from throw to throw, the answer is 3 beats, which is the same as the number of balls. And there are 3 reactions to this. One is the people who really don't understand why that's interesting. One is the people who think, well, it's obvious because, and can usually give a reason. And then there's the one that I had when I first got it. That was just totally surprising. When you see the reason why, it's not surprising. You think, well, I was stupid not to understand that. But this is what maths and physics does to you, is once you see why things happen, it becomes fairly obvious. But it's the same. The time from throw to throw is the same as the number of balls, which is just kind of cool. So with 3 balls, the cycle time, the time from throw to throw, is 3, and the flight time is 2. Why is the cycle time 3? Because the balls take it in turns. Each one is thrown every 3rd time. So what are the numbers for 4 balls? If I juggle 4 balls in the standard pattern, what are these numbers going to be? Well, the cycle time is probably going to be 4 because the balls should take it in turns. And the flight time will be 3. Well, let's try that. Here we go. Green, pink, orange, blue. Reading down the diagram, green, pink, orange, blue, green, pink, orange, blue, green, pink, orange. And the green ball has to stay in the same hand. And you will see that it is in flight for 3 beats of time. The orange ball has to stay in the same hand, and you end up with the balls bouncing over it. If I do this, if I physically do this, if I juggle those 2 in that hand, you will see the balls basically bounce over each other. It's almost like they're playing leapfrog over each other, but it's leapfrog through space. Sorry, through time, not leapfrog through space, which is kind of cool. We mix up space and time, and sometimes I get horribly confused. So here we've got the balls playing leapfrog over each other in time. If I run sideways, I can actually make them play leapfrog. I don't have room here and I would go off camera. So not going to do that. But if you look at this, you'll see that the flight time is 3 and the cycle time is 4. So these numbers, there it is running in space. So there we go. It's 3 and 4. No surprise. What are these numbers going to be? And if you said these numbers are going to be 4 and 5, think about what you've just done. You've just made a prediction about something you've probably never really seen and almost certainly can't do. Now, there may be some people in the audience who can juggle and possibly can juggle 5, in which case a lot of this will be called old news to you. I hope you're playing along anyway, because I think it's really cool, even if you know it. So here, you have predicted that when you juggle 5 balls, each ball will be in flight for 4 beats of time. Let's try it. Here's a throw. Flight time 4. Countdown. 1, 2, 3, 4. It has to land at that time. Does it land here or here? From the diagram alone, we can see on the left-hand side, at that point that I'm pointing to, I already have an orange ball and the hand is becoming empty. In technical parlance, that is a throw. The other hand is empty and is going to become full with an orange ball. That is a catch. So it has to be in the other hand. We have now deduced that when you juggle 5 balls, they must change hands. So that ball will change hands. In fact, they all change. They all change hands. And suddenly this looks like a tremendous mess. But if you pick one ball and watch it down the diagram, you will see it doing that sine wave, that elongated wave down the diagram. Is this 5 balls? It should be. But we've drawn the diagram without knowing that it's 5 balls. Let's check. So there are several ways you can check. You can count the balls in at the top. You can count the balls out at the bottom. You can try and color them all differently. You can say, well, one of them's blue and it's crossed by 4 different orange ones. Here's what I like to do. I like to take a photo. Now, a photo in a space-time diagram is a slice of time. So here we go, here's a photo. And in that photo, how many juggling balls are there? 1 in the hand just being caught, 1 on its way up, 1 in the middle, 1 on its way down, and 1 just about to be thrown. There are 5 balls in this space-time diagram, which means that these numbers are right, which is good, which is cool. And that means that we can make predictions. We can make predictions about what has to happen if I juggle 201 balls. in the standard pattern. The cycle time has to be 201. The flight time has to be 200. Now, that's telling me that I would have to do 200 or so throws per second. Now, when I juggle 5, I juggle at about 4 hertz, 4 throws per second. Imagine I could juggle at 20 throws per second. I'd be humming. 20 hertz is inside the limit of human hearing. I would literally be humming, purely because my body would be vibrating so fast to get 20 throws per second. And then how long would each ball have to be in the air? It would have to be in the air for 10 seconds. You can do the sums. You'd have to throw it over 70 kilometers an hour to be able to do this, right? Actually, to be honest, I can't remember what the numbers are. But you have to throw the ball to be in the air for 10 seconds. 5 seconds up, 5 seconds down, ignore air resistance. Do the sums. You cannot throw that far. You can't do it 20 times a second. You're just not going to do it. Interesting to question could you do it on Mars or could you do it on the moon? Certainly you can do it in the International Space Station. By the way, they say there's no gravity. There is gravity, but you're in free fall, but there is microgravity, and that has an effect. If you put two things, if you go outside the International, here's a cool thing. Stand outside the International Space Station. You'll die because there's no air. All right, wear a spacesuit and stand outside the International Space Station and hold a juggling ball right by your helmet and let it go. And you know that it will stay there. Okay, you're traveling that way, about 8 kilometers per second. Earth is in that direction. Push it sideways, very, very gently, exactly outwards. And as you know, no gravity, weightless, so it keeps going. No. It travels outwards, but it gets slower and slower and slower. And after a while comes to a stop and starts to come back again. And after about 45 minutes or thereabouts, it comes 47 minutes, I think it is. It comes back. If your throw is perfectly accurate, it comes back through its initial position. Let it. You're back inside having a coffee. But let it go by. It goes out the other direction and stops and starts to come back again. And it will do simple harmonic motion. If you got the direction exactly right, it will do simple harmonic motion. Orbital mechanics are really, really weird, really cool, deeply confusing until you've played Space Kerbal or something similar to that sort of thing. Do the sums. But it's really cool. Anyway, you're not going to juggle 200 balls in Earth's gravity in my lifetime, even though I do intend to live to about 3,000. And I look forward to seeing what the technology is going to be at that time. So anyway, that's what happens as the numbers get bigger, but what happens as the numbers get smaller? What are these numbers going to be? 1 and 2. What does that mean? Well, what that means, have I got a diagram? No, I haven't got a diagram for that one. Okay, so here we go. What does that mean? Well, if I'm juggling 2 balls and the balls take it in turns and every throw is the same, then when I throw this one with this hand, I'll throw this one with this hand, and then it's the orange ball's turn and it's this hand's turn. So that means the ball has to come back to that hand. And each ball is thrown every second time. Orange, green, orange, green, orange, green. You'll notice that my hand is empty for 1 beat and my hands are alternating. Most people can't do this without a lot of practice, because what happens is people go throw, catch, throw, catch, throw, catch. No, you have to throw with this hand while you catch with that hand and vice versa. Throw, 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 throw. I'm also doing this very slowly. I'm doing this at about 2 throws per second, slightly under. If I juggle it at the same speed as I juggle 5 balls, it looks like this. At which stage most people go, what's the point? Well, it turns out to be a critical part of the pattern of what's going on. So that's how you juggle 2 balls. What happens as you juggle 1 ball? What are the numbers going to be? If I only have 1 ball, but I have to involve both hands, and my hands have to be full half the time, the ball has to go from here to there with no gap. And back, and back, and back. This full speed is 1 ball juggling. Uniquely amongst the juggling tricks that I'm doing in this presentation, this one can be done in super slow-mo. Now, you probably think that's really stupid, but I just had most of you sitting there silently watching me. Actually, you're probably thinking, is my Zoom frozen? But anyway, that's one ball juggling at full speed. It just goes from hand to hand. So here we go. Number of balls, 0. What will the cycle time be? Now, if you follow the pattern, the cycle time has to be 0. What's the flight time going to be? If you follow the pattern, the flight time has to be -1. The ball has to be in the air for a negative amount of time. That means that you throw the ball and catch it earlier. I mean, think about it. When I'm juggling 3 balls, I throw the ball and 2 beats later in the future, it comes down. You know, time is a vector. It has a direction. I throw the ball. If I'm juggling 5 balls, I throw the ball 4 beats later, it comes down in the future. I juggle 2 balls. 1 beat later, it comes down in the future. I juggle 1 ball. It comes down immediately. I juggle 0 balls. Every ball that I'm juggling has to go. You may think that saves you. What this says is that every ball you're juggling, when you throw it, has to go backwards in time, but you're not juggling any balls, so that's okay. It's vacuously true. You may think that time travel is not actually essential. I've got news for you. It is. And I am going to perform the time travel of a juggling ball. It has to occur in a non-standard pattern, but you are going to predict the existence of a juggling pattern that requires time travel of a juggling ball. I'm going to start by juggling 4 balls. I've marked one of them there, but what's happening here is the balls take it in turns. So I get yellow, orange, pink, green, and then I go back to the yellow. So juggling 4 balls, remember 2 balls, when I'm juggling 4, I do 2 in each hand and they kind of bounce. So this is juggling 4 balls. So there they are, bouncing in the hands. And each ball has a cycle time of 4. If you look at the orange ball, it goes orange 2, 3, 4, orange 2, 3, 4, orange 2, 3, 4, orange 2, 3, 4, orange 2. So each ball has a cycle time of 4. But what I claim is this. When I throw the balls, I'm throwing them into the future. But I don't have to throw them all the same distance. So think of 2 balls. Think of the orange and the green. Normally, they would come down in the same order that I threw them. I would throw the orange one first and the green one after, and they would come down in that order. I don't have to do that. I can throw the orange one further into the future to the point where the green ball would normally land. 1 beat too late. And then I throw the green ball short to fill in the gap left by the orange ball. So I throw the green and the orange, but I throw the green orange first. I throw the orange one too far and the green one not far enough. And if I look at how far they go and look at their cycle times, I get 5-3. So here we go. Let's do that. In the middle of juggling 4 balls, I will throw the orange one as if I'm juggling 5. It will go high and crossing. I will throw the green ball as if I'm juggling 3. Now, because of the limitations of the camera height, etc., you might get the 5 go off the top of the screen. It's going to be the same one. I don't have a ball up there that somebody's going to drop for me. But here we go. Orange high, green low. Let's see if I can make this work. Lighting's not perfect, but we'll see what we can do. Orange ball high, green ball low. Counting down so you can see when it comes. 3, 2, 1. High, low. And again, this time throwing the green ball high. 3, 2, 1, high, low. And again, oh, very ratty. Let's try that again. Orange ball high. 3, 2, 1, high, low. High, low. So you can see that I can do a 5-3 in the middle of juggling 4 balls. Why only throw one of them too far? Why not throw 2 consecutive throws too far and have a third ball then fill in the gap that you end up with? And that gives us a 5-5-2. So what I'm going to do here is I'm going to throw, actually just drop out the pink one and use white. It's a much better discrimination. So what I'm going to do here is I'm going to throw the orange one high and the green one high, and then with the white ball do a 2. Remember what a 2 looks like? It looks like this. Now, if you think in the middle of juggling 4 balls, I'm going to throw 2 of them really high and crossing, I'm going to go with this one. No, you're crazy. What I'll do is I'll hold it up to show you. It won't be for very long, but I'm going to do 2 high throws and hold up, display the white ball. That's when I would do a 2, but I want to show you the white ball. So here we go. Orange and green going high and the white ball being displayed. 3, 2, oh, sorry, lost it. Quite tricky to do this. 3, 2, 1, 5, 5, and there's the 2. Let's do it again. This time green and yellow, and there's the 2. Let's do it again. This time yellow and orange, and there's the 2. If you're worried that the white ball hasn't had a chance to play, I can throw the white ball and hold up something else. So in the middle of juggling 4 balls, I can do a 5, 5, 2. What comes next? Should be 4 numbers. It seems reasonable to have 5, 5, 5, and a 1. For me, the really cool thing about this is that until we invented this notation, as far as we know, nobody in the world had ever juggled 5, 5, 5, 1. I remember taking this to a juggling convention, going to a juggling convention and getting hints for how to learn 7, and going up to somebody and saying, yeah, please show me. Actually, it was still 5 at that stage, saying, please show me some exercises to do for 5. And they helped me and they were really cool. And then I said, oh, here's a 4-ball pattern that you might like. And I showed them this and they couldn't do it. So what is it? 5, 5, 5, 1. So let's try and do that. Starting with the yellow ball, counting down, 3, 2, 1, 5, 5, 5, 1. Now, that's over very quickly. Let me do it again, starting with the green ball, 3, 2, 1, 5, 5, 5, 1. Now, that's over so quickly. Let me try and do it for you constantly. This doesn't always work, but let's have a go. 5, 5, 5. Oh, I told you it didn't always work. Good job I didn't leave my coffee there. Here we go. Let's go again. 5, 5, 5, 1, 5, 5, 5, 1, 5, 5, 5, 1, 5, 5, 5, 1, 5, 5, 5, 1, 5, 5, 5. Oh, I lost it. Never mind. Okay, so you can see there that 5, 5, 5, 1, it works. It actually works. In fact, it's a brilliant pattern for practicing 5, because when you're juggling it, 3 out of every 4 throws that you do are exactly the kind of throw that you need to do for juggling 5. That's the whole point. To be honest, don't care what comes next. 5, 5, 5, 5. Time travel. So if you follow this sequence, you have to agree that there should be the time travel of a juggling ball, which is just wonderful. Yeah, how do we do that? Okay, so let's draw the diagram. Space-time diagram is your friend. So here we go. What was rule number 3? Bet you don't remember. What was rule number 3? Rule number 3 was that the hands alternate. So I'm going to mark on the thing I care about, which is the throw. There's the throw, okay? In each throw, my hands alternating. And I'm going to be juggling 4 balls, and then I claim I'm going to do 5, 5, 5, 5, 0, whatever that is, and then go back to juggling 4. Now we know that the 5 will change hands. Each 5 must change hands. Each 5 must change hands. The 4 will bounce in the hand. Remember, 2 in one hand, like they're playing leapfrog. Each 4 will bounce in the hand, including the ones leading into the pattern. How often are my hands full? Knee-jerk reaction, Pavlovian response. How often are my hands full? Half the time. I need a juggling ball here. The cycle time is 0. The flight time is -1. That ball has to go backwards. Every throw has a catch. Every catch has a throw. It's almost like it makes sense. It's a Feynman diagram. Let's count the balls. Let's take some photos and count the balls. Green, orange, pink, and blue, 4 balls. Green, orange, pink, and blue, 4 balls. Count them down here. Pink, blue, green, and orange, 4 balls. Count them here. There's the blue and the orange. That's 2. There's the pink and the green, another 2. There's the red ball in my hand here. That's 5 balls so far. But by the conservation law of juggling equipment, we should have 4 balls. So that means that this ball here is a negative ball. So in my diagram, a ball going backwards in time is the same as a negative ball coming forwards in time. So if we have a look at this thing here, what we have is an antiball. We have the mutual creation and annihilation of a ball-antiball pair. And some people go, hang on a minute, that can't happen because we're getting lots of energy. You know, if you've got particles coming into existence, there must be energy. But as you know, we have a quantum uncertainty principle between position and momentum, but we have a quantum uncertainty principle between energy and time. And if we've got a very small uncertainty in the time, which we have because we know exactly when the throws and catches are happening, we've got a very large uncertainty in the energy. So we can borrow from the quantum uncertainty in energy to create a virtual ball-antiball pair, so long as they mutually annihilate each other within the uncertainty period, so long as you don't do it next to a black hole where one of them might fall in, the other one pop out as Hawking radiation, which would be amazing. But the truth is that I lied to you. Requires mass and E equals mc squared, but we can actually use the quantum principle to create the energy that we need in order to be able to create the ball-antiball pair. Well, in truth, I lied to you. In truth, what happens is I say that my hands are full half the time, but I create an antiball to cancel out the ball that should be in my hand to create an empty hand. So the boring practical case is that I have 4 balls and I throw them high into the air and this hand is empty for that one beat. But if you listen closely, you may hear the small thunderclap of the ball-antiball pair mutually annihilating. Starting with the orange ball, 3, 2, 1. And at that moment, my hand is empty when normally it should be full. Let's do it again. Here we go. Starting with the green ball, 3, 2, 1. High five. So you can see there that I really do have an empty hand for that one beat. And a lot of people, in particular, a lot of more practical people go, well, what's all this nonsense about balls and anti-balls and blah, blah, blah. But as you know, Gell-Mann predicted the existence of particles by following mathematical patterns. The classic one, of course, is Dirac with the positron, saying that the positron should exist before it was actually discovered. And this is what we do in particle physics, is we have the structure of the particles, and then we go hunting for them, and we find the evidence for them, and then people go, yeah, that's not very good evidence, and then we look again. Following patterns, making predictions, testing those predictions, that's what science is about, even though it's so complex, it's not as clear as that. Here in the juggling, it's perfectly clear. This is exactly what we did. We discovered new juggling tricks by following that pattern, which is just kind of cool. So 55550 does exist, can be done. In fact, this one was known, but fitting it into the theoretical framework is the stuff that we did. And it's just wonderful stuff, the fact that we can do this and the fact that we get the patterns popping out. Now, I promised you this diagram. Now, I don't know, Jonathan, can we have, we don't need to run polls, but in the comments, what I want to do is explain this diagram and then get people to vote just as a sort of a comment blast, so they can type in their comment and everybody hit enter at the same time. And I think you can do that in the YouTube comments. Yeah, that work?
Yeah,
okay.
We can do that.
So what we're going to do
just
is
Colin,
this diagram.
1 second. Just for you to know, there is a delay between you and the YouTube stream for about 10 seconds. So when you say go, they're going 10 seconds
okay.
before they can do anything.
We'll allow for that. We'll allow for that. Okay, super. So the way this diagram works is we start with the cell, the 0, 1, 2 cell. Ignore the red numbers; they're just placeholders. Actually, they're not just placeholders, but ignore them for the moment. And what we need to do is follow the black arrows and write down the black numbers as we go. So you'll see if you start from that cell at the top, you can follow the arrow marked 3 and come back to where you are, and you write down the 3. So you go 3, 3, 3, 3, 3, 3, and that is the classic 3-ball juggling trick. So now I'm going to give you the choice of what to do next. Let's leave that place. And you can either do a 4 going sideways or a 5 going down. Make up your mind, pick one, do a YouTube blast. I'm going to count down. 3, 2, 1, go. And now I have to wait for 10 seconds, but that's fine. I'll wait for Jonathan to tell me if he's got a clear winner out of 4 and 5. I'm going to take another drink of water. How are we doing?
We are going with a 4.
Okay, so we've got a 4. So that means we're now at the cell marked 013. By the way, start to think in advance a little bit. You don't necessarily want to get boxed in a corner or whatever, but it's entirely up to you. From 013, you can either do a 2 to go back where you came from, do a 4 to go down to the bottom level, or a 5 to carry on in the same direction. 3, 2, 1, go. 2, 4, or 5.
Two.
We've got a 2. We're going back to where we came from. That's really unusual. I don't think I've ever had a group choose that. Okay, so here we go. What does that look like? In the middle of juggling 3 balls, what I'm going to do is I'm going to throw a 4, which means to throw it so as it comes back to the same hand. And then in the other hand, do a 2. And I do that just by displaying the yellow. So I'm going to do it with the green here and the yellow here. So here we go. Next time round, we get 4, 2, 3, 3, 3, 3, 3. And again, next time round, 4, 2, 3, 3, 3, 3. Now you'll notice that I didn't hold up the yellow. I held up a different one that time. If I always do the green as the 4, then that it becomes a different ball in the other hand each time. If that's always that, then I always change hands. And that's because the balls are changing their ordering as I do them. So here's one of my favorites. What I want you to do is I want you to have a look at the diagram and see if you can see the arrows starting from the cell. Follow this sequence: 4, 5, 1, 4, 1. Across, across, return, down, and home. And so what that ends up being is 4, 5, 1, 4, 1. Let me show you that, starting with the orange ball from this hand, and we end up with 4, 5, 1, 4, 1. And if I do that constantly, I get 4, 5, 1, 4, 1, 4, 5, 1, 4, 1, 4, 5, 1, 4, 1. Look, the green ball is always green. Well, of course, it doesn't change color, but it's always the green ball going over the top. And that's because that's the ball that is the 5, so it will repeat every 5 beats, and the pattern is 5 beats long. So it will always be the same one. And following the orbit of a juggling ball through a pattern is a classic thing that we can do to try and analyze what's going on. This is just a small portion of an infinitely large diagram. And you'd think I would need a different diagram for 4 balls and a different diagram for 5 balls. But in fact, what we do is we take the infinite diagrams for each numbers and then run it backwards to the infinite diagram for 0 balls, where we make ball-anti-ball pairs on demand. And then if we take a finite portion, we can then add on the number of balls that we want to cancel out the anti-balls. There's a bunch of structure going on here. There's some really cool stuff happening underneath all of this. But I hope that's shown you that there is some really unexpected maths going on here. Nobody would have thought that there was this kind of diagram, that we could create those sorts of patterns out of this. Some of the patterns that we've created, never been done before. Some of them are mind-numbingly tedious and you would never want to do them. But they exist and they fit into this structure that we've got. And that's the cool thing, is there's a lot of structure happening underneath here. And this has given us a great insight. There's more. I haven't talked about what happens with hand movements. I haven't talked about timing shifts. I haven't talked about synchronous throws. I haven't talked about more than 2 hands. All of that has been done in the last 20 or 30 years since this was first found. But this is just the briefest of introductions. And I hope you have found that slightly weird, slightly intriguing, a little bit odd, and at times entertaining. And I want to say thank you again so much for having me here. I hope you've enjoyed that. Thank you very much.
Thank you very much, Colin. I've unpinned myself, or unpinned you, so people can see who's asking the questions.
Sure.
First of all, just a small review from the chat during your talk. The worst part of this being an online talk is that we can't clap after every trick.
It's really weird giving an online talk because you're used to hearing people go and hear people going when you tell a bad joke. You know, you're used to getting that little bits of feedback, and it's nice to get applause at the end. Although, to be honest, it can be slightly embarrassing to get applause at the end because, you know, this is just stuff that I love. So, but it's nice when people appreciate it, and that's the way they show it. So that's cool.
Sounds great, Colin. We really enjoyed it. A few more things happening in the chat. I'm loving the showing off. And then begins the questions. There's a lot of people in chat writing right now that this is the most amazing thing they've ever seen. That was really cool. Damn. Thank you so much. This was one of the most amazing talks I've ever seen. People are really enjoying it. We're really happy to have you here. So, questions. Let's see, the first one here. In the beginning of your slides, you had some theorems written.
Yep.
Yeah.
So let's go back to the very beginning and just show you this is a fairly simple theorem, although it's a bit unexpected. It takes a bit of a setup. So I've got this is the basic setup for this. So take a finite set of integers. So the Z with the double bar is the integers. A is a set of integers, and the size of A is finite. So any finite set of integers, you know, you might take minus 8, 7, 23, 101, 102, 103, yeah, any finite set of integers, and take a function from the natural numbers, the counting numbers, to that. And you can think of this as basically taking the numbers you've got as a sequence, not necessarily in order, and possibly with repeats. That's what the second line means. And then take a slab of them from the 8th position to the bth position, not including the bth position. So take some of them. And then the last line just says take their average. So this is the formal setup to say, take a sequence of integers where all of those integers are chosen from a finite collection. And when I take a collection of them, of that sequence, take their average. So for example, I could just take the digits of pi. I could take 3.14159265358 and so on. That might be my sequence. And my finite set now is just the digits from 0 through 9. And I can take the average. If I take the average of after the decimal point, the next 3, then there's 141. So the average of those is 2. So what I have there on the bottom line is A takes the average of the value of the sequence F over an interval. Okay? So if I take a sequence of intervals that get longer and longer and longer, is there anything that we can say about the average that you get? And the answer is no. You can make that do anything you want. But here's the thing. If I say that the only time that A plus F of A equals B plus F of B is when A equals B, that's a slightly weird condition. Takes time to think about it. But I'm now going to make A satisfy the condition that, sorry, F, my sequence, going to make F satisfy the condition A plus F of A equals B plus F of B only when A equals B. The interesting thing is that this average converges to an integer. And that is weird and slightly surprising. And the best proof that I know is that any sequence of numbers that satisfies that condition can be interpreted as a juggling trick. And the average is the number of balls you're juggling, and therefore is an integer. So that's the bit of maths that I had there. And then I also showed you, gave you a pre-sequence of the diagram that I had later on. So yeah, that's the mathematical theorem that I have here, is that about the average of sequences.
Great answer, Colin. Thank you very much. The next question here, do you know of, or does there even exist a mathematical group that describes the symmetries in juggling?
There are different types of symmetries that you can think about. And when you talk about symmetries on a plane, mathematicians know that there are 17 symmetries on a plane. When we start to do this in 3 dimensions, because we've discretized space or discretized time and space, the symmetries that you get are really not very interesting. They're all very, very elementary. You can start to talk about a group theory structure. So when I do a juggling trick, I permute the balls. And you saw that with 4-2. There's a permutation of the balls. And you can say, do this trick, then do that trick. And that's following this permutation by that permutation. And it turns out that the juggling doesn't give you anything new in that either. So people have pursued that, and it may just be that they haven't found a really cool way of looking at it. But everything that we've done with group theory and symmetries for what's turning up in juggling tricks so far has been pretty boring. Group theory, and in particular groups of symmetries and similar, is incredibly powerful and incredibly rich. And it would be very, very surprising if something as simple and elementary as juggling actually explored some of that wealth. I mean, the symmetries that you get when you're talking about the classification theorem for particles and similar sorts of things with SU3 and so forth, that's actually fairly elementary group theory. It's mind-bending because it's not obvious rotations of stuff in space. There's more going on. But we haven't found anything really cool in the juggling yet. Maybe it's still there to be found. Maybe we just haven't stumbled across it.
Again, an excellent answer. Then there is a request. If there isn't a book about this, please write it.
I started writing one a while ago. There are 3 problems. One is finding a publisher. I mean, you can just sort of open publish and so forth, but there's a lot of this stuff already available on the web. And it can be tied together. I mean, you can say this is a book. This has all of the material in it. But without the visual juggling, it's really tough. So you want it to be kind of online with animations, and people have done most of that as well. So the question is, what could I do that would really enhance beyond what's already there? So I have been thinking about this. I've been thinking about this a lot, more so over the past 2 years, as we've had the COVID restrictions and everything else, or 18 months. So I've been thinking about it. If people want to send me an email, let me pop to there. If people want to send me an email and ask me questions, then I can certainly answer questions. But there's a lot of material already available. And there's a bunch of stuff on my website about the material I've given you here. And as you start getting beyond that, it starts getting much, much more niche. And it's easier to then to hunt on the web for existing stuff. Very kind of you to say that you loved this enough that you'd really like a book. And I am still seriously thinking about doing that. Not yet.
Thank you very much. I'm sure that cleared it up. And then if you would like to go to your diagram with all the arrows.
Yep.
Because there's a question here. What was the red numbers in the diagram again?
Cool. That's a great question. So when you think about this as throwing the ball to yourself in the future, which seems like an obvious thing to do, but what you're doing is you've got times when the throws happen, Who cares if they're left hand, right hand? This works for the extraordinarily gifted three-handed juggler. So you have the times when the throws happen and you just mark them left, right, left, right. Don't care, we can ignore that. So what we're talking about now is that the black arrows are how far it goes forward in time. So what happens when I'm juggling 3 balls, I am committed now to be throwing a ball, and I already have a ball scheduled at time 1 and already have a ball scheduled at time 2. So the ball I'm throwing now cannot be thrown into cannot be thrown into time 1 and cannot be thrown into time 2. So the red numbers in that little box there are the forbidden throws. And if I throw a ball 3, that goes into time 3. And so now I've got scheduled balls at times 1, 2, and 3. And time moves on. I move forward on this diagram, or I can think of those scheduled slots as coming back to me. So having balls scheduled for times 1, 2, 3, that becomes time scheduled for 0, 1, 2. And that's why I'm back where I started. Now, if I do a 4, that means I will have balls scheduled now, because that's the one I'm throwing, times 1 and 2, because those are the ones already in the air, and time 4, because that's the one I've thrown. And looking into the future, I've got balls scheduled at times 1, 2, and 4, but they come to me, or I go to them. And that gives me balls scheduled at times 0, 1, and 3. And so the arrow marked 4 takes me to the state marked 0, 1, 3. So coming out of 0, 1, 3, I can have an arrow marked 2 because it's not forbidden. And I can have an arrow marked 4, and I can have an arrow marked 5. I can have an arrow marked 6. And where that would take me, I would then have balls scheduled for times 1, 3, and 6, which would come into me, which would give me at the state 0, 2, 5, which is not on my diagram. But that's how I can then start to extend my diagram to include larger throws from here. So the red numbers are the forbidden numbers. And the one exception to that is if I am not forbidden to have a 0, I must do a 0, because that is, I have no ball scheduled now. I don't have a ball. So I have to throw a 0. So you can see in the cell in the middle of the right-hand side, there is the schedule 1, 2, 4. So that has to become 0, 1, 3. And there is an error on this diagram. And that is that on the left-hand side, there is also a 1, 2, 4, and that should not be a 1, 2, 4. That should be a 2, 3, 4. So that's a mistake. But that's what the red numbers mean.
Okay, perfect. Thank you very much. And then there's another one. Wouldn't an article be easier to publish than a book?
There are, again, lots of articles. In fact, we've published Joe Bueller, Dave Eisenbud, and can't remember the other author, and I, 4 of us, published, Ron Graham, Dave Eisenbud, Joe Bueller, and I published an article on the theoretical foundations of juggling. There's a real challenge because you kind of want to hit the popular juggling math vibe. You don't really want to get too deep into the theoretical structures of the mathematics, but you also don't want to have to coach people through how to learn to juggle. So it's hard to figure out. But yeah, I've got, again, on my website, there are a number of web pages which amount to articles describing most of what I've talked about here. Although here I've emphasized the modeling aspect of it to try to point out that this process should feel familiar and has parallels with when you do, especially particle physics, when you do that sort of thing. So what I've written has less of that emphasis in it. But yeah, there's these days it's hard to know, because the web, it just subsumes so much. It's hard to know where to publish, how to publish, what to publish, what depth, what level, and so forth. And if you do it on the web, as I say, duplicating a lot of stuff that's already out there, if you try and get it into hard copy. Lots of people don't get hard copy anymore anyway. They expect a version on the web. So it's tough. Publishing is a really, really weird place, is in a weird place at the moment. So much stuff is behind paywalls because it takes time and effort to write stuff. Where is the reward for the people who've written it? And if it's not behind a paywall, there's no reward. But a lot of people come across a paywall and say, I'm not going to pay. There's enough stuff that's free. So it's a really difficult place to be at the moment.
Thank you. Right now, there isn't any more questions in the chat. So I will give them 15 seconds for the delay. And then if there are any final questions, if not, I think we will say thank you, but let's give them the time. It's
been a pleasure. Let me also say to the audience, it's always odd when a speaker stands up and says, I want to thank the organizer, but trust me, the organizers have done an amazing job to make this possible. So I thank the organizers because without them, this wouldn't have happened. And they've done an amazing job. They've been really helpful for me because I got weird technical requirements and so on and so on. So they've been extremely accommodating, very friendly, amazing stuff. So thank you, Jonathan, and the team behind you as well. You've been amazing. So please, people, appreciate your organizers. They deserve all of the appreciation they can get.
Thank you so much, Colin. I can see there are things coming up in the chat now, actually. Can you do the 5-ball or even 6 balls or even 7 balls juggling tricks now? Can we see you do it?
I can attempt 5. One of the problems that I have, I don't know if you can see it, this is a wall here. And I can't turn the camera around because there's other stuff over there. So one of the problems I have, my 5 is a little bit undisciplined at the moment. And 5 is the most I can do at the moment. But I have a problem that the wall is surprisingly worrying when you're juggling 5. If I hit the wall with my hand, it hurts. But I can have a go at doing 5. It won't necessarily last for very long. But and it goes off the top of the screen. But here we go. My biggest problem is I'm trying to keep it low and tight, and that means I get more collisions. But there you go. There's 5 being juggled. I'm not a numbers juggler. I used to do 7. I mean, it's when I for a magical 6 or 8 months in 1985, I could juggle 7. Right. So that's a very long time ago. And without constant practice and consolidating, it kind of disappears. My favorites, though, are really the small stuff, the 3-ball juggling. And in particular, one of the ones that came out from the theory that hadn't been known, that I used to torture 7- and 8-ball jugglers, is 4-4-1. You find it on that diagram that's on the screen. Go sideways, then down, then back to home, and you get 4-4-1. That's throw one up, pass one across, and then repeat. And the thing about that is each ball does exactly the same thing. It bobs up twice, then changes hands. And yet they all mesh together to make this lovely little 3-ball pattern that is torturously difficult for people who don't do this type of juggling. So that's great. Anyway, that was a quick burst of 5. There's no way I can do 6 in here. I had a go at doing 7 the other day outdoors, and yes, I think probably with about 60 hours practice, I could probably get it back. But it's a long way off.
I think with that, Colin, there is no more in the chat. So we would like to say thank you very, very much for all of us in the organizing committee, and especially from all of our wonderful viewers right now, all of our attendees. Everybody really enjoyed it a lot. So thank you very much.
It's been an absolute pleasure.
Excellent. That's even better then. Then we will go to the jingle. And after that, on this Zoom call at 5 o'clock, there will be a workshop in science shows. I mentioned this because there's also the workshops in Gathertown. Okay. So thank you very much.
Absolutely.
And go to the jingle.
It's the time of the year to get together. Sadly, this time around virtually. Let's make the most of it, we always do. Hooray! For ICPS 2021. For exciting days are ahead of us. We've been waiting for this so long. Let's connect again, our physics friends. Cause it's ICPS 2021. Let's take our time to gather all the knowledge. Brilliant speakers, we share it just with you. Collaborations, friendships, and so much more. Hooray! For ICPS 2021. For exciting days are ahead of us. We've been waiting for this for 2 years. Let's connect again, our physics friends. Cause it's ICPS 2021. Let's get to it, it's gonna be fun. ICPS. Hooray!